MJO in terms of precipitation over a particular region. And when you use those techniques, that amount turns out to be 40 to 50%. So this is a really surprising number that people used to think it is much smaller. Okay. And MJO is such an important and easy to detect phenomena that you can actually see it in winds and precipitation. So U stands for zonal wind. 850 is 850 hectopascal. So it's the zonal wind at 850 hectopascal. So x-axis here is longitude in both panels, and y-axis is time, correct? X-axis is longitude and y-axis is time. And if you look at those carefully, what you will notice is that there is sudden red spots. So reds are westerlies, meaning that the winds are going from west to east. And you will see that signature in the precipitation also. And if you look at those, for example, if you look at those white lines, those provides the propagation speed from west to east. So if you look at the slopes and estimate the propagation speed, what you will get is roughly about 5 meters per second propagation speed. So MJO propagates from western part of maritime continent to the eastern part, let's say, with a speed of roughly about 5 meters per second. And of course, because you have topography and land over the maritime continent, it actually affects the MJO. And it turns out about 40 to 50% of the MJO are kind of stuck within the maritime continent. Okay. So for today's talk, I am going to focus on three topics, all related to land-air-sea interaction or land-atmosphere interactions. So the first one is role of land-sea contrast on the precipitation. And specifically, what we are going to see is how individual islands within Indonesian maritime continent actually impacts other islands, correct? So how, for example, how Sumatra influences, let's say, Borneo or New Guinea, or how Borneo influences Sumatra or New Guinea. So that type of numerical experiments I'll conduct. Then we'll also look into a little bit on role of topography on diurnal cycle of precipitation. And finally, this is a really new idea, the last part, where I'm going to talk about how precipitation can actually cool down the surface in the maritime continent, and eventually how it can impact precipitation in the maritime continent. Okay. So I think you guys all are, so the motivation of the first part comes from elephants in the maritime continent. So one question that people get is, how did elephants get to Borneo? And this is a really interesting paper came out a couple of years back where they looked into the origin of elephants, correct? So, for example, how elephants actually reached Kalimantan or Borneo, basically. And so there used to be a lot of different hypotheses, like, maybe humans introduced it, or maybe through some other processes. But the actual reasoning was very, very simple, which is that they were not always isolated islands, correct? So for example, at present day, this is the geography looks like. So you have here Sumatra, Kalimantan, and then you have now New Guinea. But if you go back, let's say 10,000 years back, which used to be called Sunda Self, around 11 to 14,000 years back, and those were all connected, correct? So it was very easy for the elephants to, for example, reach Kalimantan, all right? So the reason I'm giving this example is when the whole area was a single landmass, how was the precipitation at the time, correct? And there was a really nice paper by Sar et al. So it's a kind of a paleo paper where they looked into precipitation over Sunda land, and what they found was that precipitation used to be much, much stronger over Sunda land, correct? And because the precipitation was so much stronger, all the forests in maritime continent used to be much more dense, and the trees used to be much taller than what you see actually now. Okay, so it's a very interesting idea. So I, I really like that idea, and I thought that, okay, let's try that concept at present and see what would happen if one of the islands were not there, correct? Or if one of the islands were inundated, then how it will actually influence other islands. Okay. So the question that I'm going to ask is how an individual islands may impact precipitation over other islands and the entire maritime continent, and if there is any specific pattern in the change in precipitation. Okay, and you will see what I mean by that. Okay, so this is obviously we can do it only using numerical modeling. Correct. So I'm using a very popular model in the meteorology community, which is weather research and forecasting model. I'm using 12-kilometer grid spacing. So this may be a little bit coarse, but it's good enough to separate the land and sea. So I think for our purpose, 12-kilometer is actually a quite decent resolution. And there is a common weakness that we have in numerical models, including the weather research and forecasting model, is that it typically underestimates precipitation over ocean and overestimates precipitation over land. So this is something you'll have to keep in mind. There is a weakness in the model, and I'm using several other data sets to basically run the model, and so I'm not getting into details of those. Okay. So what we do is we choose a particular time to run our simulation. So in this case, I'm choosing April 2009 because there was a strong MJO event, and I'll explain why an MJO event is useful in terms of doing this particular experiment. So this is a typical way we show how the MJO propagates. So basically, if you see that it is going like this outside this circle, then that means that it is actually a strong MJO event, and if it goes throughout it, then that basically means that the MJO was able to propagate throughout the maritime continent. So it didn't get stuck in the maritime continent. And this is basically the same figure for zonal wind at 850 hectopascal and precipitation. And you can see that the zonal wind moved towards east and precipitation also moved towards east. That is associated with the MJO. So these are the three experiments that we are doing in numerical experiments. So the first experiment is a control experiment where we have realistic land over the maritime continent. So I'm calling one experiment, I'm calling it as E1L, where I actually remove Sumatra. So there is no Sumatra in our model, and we run the model to see how it influences the maritime continent precipitation. In the second experiment, I'm removing Borneo and Sulawesi and looking into how it actually influences precipitation over other islands. And in the third experiment, we are actually removing New Guinea to see how it influences the precipitation over other islands. Okay. And again, the whole motivation comes from the fact that once upon a time, all these islands were connected, correct? So you had a lot more precipitation. Now we are removing one island at a time. So the expectation is that precipitation should overall reduce because we have less land mass in these experiments. Okay. So for all our analysis, we are using something called moisture budget equation, which basically explains what determines precipitation. So in this equation, you see that P is for precipitation. So if you bring all the other terms to other side, they will become the mechanisms that will explain precipitation. So this is a moisture tendency, so how humidity changes as a function of time. This is V, which is the velocity component. Delta Q is the gradient in humidity. So this is basically your horizontal moisture advection. This is your vertical moisture advection. So this is vertical velocity, and this is how the humidity changes as a function of height, or in this case, as a function of pressure levels. This is evaporation, this is precipitation, and then for most of these equations, they don't balance, so you'll actually have to add another term, which is the residual term, to basically balance the set of equations. So what we'll do is basically we'll try to explain what determines precipitation in this set of experiments. Okay. So this is one of the main results of our study. So at the top, the three experiments, one, there is no Sumatra, there is no Borneo, and then there is no New Guinea. Okay? And this is from the control simulation. So the blue basically means is the land precipitation. What is the land precipitation rate? And it turns out to be roughly about 12 millimeter per day. The red is ocean, and then the green is the average, the entire maritime continent, okay? Which is what you would expect is that land precipitation is more, so the model is actually getting that correctly. Your ocean precipitation is less in terms of rate, and then land overall precipitation is somewhere between the blue and red, correct? And the reason this green is close to the red is because there is more oceanic area within this box, so it is actually close to the red line. Now, when you remove Sumatra, what you notice is that your blue line actually decreases. So the overall precipitation decreases, which is what you would expect with the removal of land mass. When you remove Borneo, you also see that there is a decline. When you remove New Guinea, you also see there is a decline. Okay? So it turns out that the strongest impact is when Borneo and Sulawesi islands are removed. It's 30% less over land and 20% less over ocean. So what it tells you physically is that island size alone does not play the key role in total precipitation. For example, Borneo is much smaller in size compared to New Guinea, but Borneo's impact was actually larger than New Guinea impact. And we'll explain why that may be the case. And ocean precipitation was also reduced in all this experiment, and it is most dominant when Borneo was removed. So for example, if you look at those red lines, this line is the smallest one, meaning that Borneo ocean precipitation was reduced most when Borneo was removed. And the reason for that is because Borneo is one of the islands where there is a lot of offshore precipitation, meaning that those clouds actually move from Kalimantan to the ocean and then it rains. So something which you don't see much over, for example, New Guinea. New Guinea, everything is coming from the ocean to the land. In case of Kalimantan, you actually have a lot of offshore precipitation that goes from the land towards the ocean. So you'd expect ocean precipitation to decline most when the island of Kalimantan is actually removed. Okay. So the question that we are asking now is, how do these results depend on background winds? For example, during MJO and non-MJO period. So during MJO period, maritime continent has westerly winds, and during non-MJO period, you actually have easterly winds. So if you separate those westerly winds and easterly winds, you can literally separate when there is MJO and when there is no MJO. Okay. So let's just focus on this right-hand side. What you are seeing here is that how the precipitation changed when you actually have background westerly winds. In other words, when there was actually MJO in the simulations. So the top panel is the difference between removal of Sumatra minus the control. And you can see that over the Sumatra, there is actually a lot less rainfall. That's what you'd expect. If you remove the island, there will be a lot less rainfall. This is when you remove Borneo, and you can see that precipitation was negative, meaning that precipitation was a lot less compared to the control simulation. And this is the removal of New Guinea island. And you can see that there is a lot less precipitation, which is obvious. But what we see is really interesting is when you remove Sumatra, what happens to Borneo and New Guinea? And if you see closely, what you'll notice is that there is an increase in precipitation over Borneo by and large, and there is also an increase over New Guinea, correct? And we'll explain why that may be the case. So just to summarize here is that removal of islands cause a change in other islands' precipitation. There is no doubt about it. And during westerlies,